Hello, my name is Ganepola. I am a geoengineer, urban risk management specialist at Asian Disaster Preparedness Center, Thailand. Title of my presentation is Effects of Root Tensile Strength of Vegetation on Slope Stability. This is the outline of my presentation and I will be elaborating under each of the following topics. Numerous research studies affirm the positive role of vegetation in mitigating shallow slope instabilities. Some of the main functions of vegetation that contribute to increase the slope stability are protection against erosion by surface water runoff, roots reinforce soil layers, root water uptake and evapotranspiration dissipate excess pore pressure and establish sufficient matrix suction, plant canopy foliage intercepts rainfall and armor the slope against surface erosion from rain splash. This field of science, where plant materials are used to serve as soil reinforcements and barriers to earth movement, is known as soil bioengineering. These techniques have been recognized as an ecologically and environmentally friendly technique that can positively affect the stability of slopes. However, application of soil bioengineering techniques is still limited in the Sri Lankan context. One of the major limitations is the unavailability of proper records on bioengineering properties of plants in Sri Lanka. This study investigated root tensile strength of 15 plant species commonly found in Sri Lankan hill country and the influence of root tensile strength on slope stability by computing the shear strength increase offered by plant species. Now we will look at the method from literature we used to evaluate the effects of root tensile strength in slope stability analysis. In literature, additional soil reinforcement by plant roots has been incorporated as an increase to shear strength. According to Walden and Dakasian, the soil reinforcement due to plant roots can be directly added to the Coulomb equation subjected to the assumptions given here. Wu et al. And Gray and Sothir elaborated on a force equilibrium model to calculate the additional shear strength provided by the roots from full mobilization of root tensile strength, which is given here. Further, they said that the value of sine theta plus cos theta tan phi is relatively insensitive to normal variations in theta and phi. An average value of 1.2 was proposed for the term. Chavez et al. Mentioned that experimental studies had revealed an overestimation of the role of root reinforcement in soils based on the above model. They indicated a correction factor of around 0.4 would be needed to revert them to experimental values. Hence, the equation can be simplified as given in the slide. Method of study. First, we did a collection of root specimen. Root samples were collected from natural landscapes in hill country districts as well as from Candian home gardens. The roots were manually collected by careful excavation or by cutting the roots on exposed profiles. After excavation, the roots were individually stored in a plastic bag to preserve their moisture content. The collected root samples were then immediately transported to the laboratory for tensile testing. After that, root tensile strength tests were conducted in the laboratory using the universal tensile and compression test machine. In this experiment, cotton textile bandage was wrapped around the gripping ends of the roots to increase the grip and to minimize the damage to the roots. The initial root length was set to 150 millimeters. The root diameter was measured at both ends and the middle using a vernier caliper. The maximum force at the breaking point was recorded, and this equation was used to calculate the tensile strength. After obtaining the test values from the laboratory, the effect of root tensile strength was modeled as follows. The increase in shear strength or the root cohesion was calculated using the equation given for the tested plant species. Considering a planting configuration of species parallel to slope contours, a two-dimensional slope stability analysis was carried out. An average value of root cohesion for the entire slope was calculated considering the spacing between each plant row, as suggested by Mahanopkul and Jyoti Sankasa. This root cohesion was incorporated into conventional limit equilibrium analysis as an increase in effective cohesion in order to determine the factor of safety of the vegetated slope. This table summarizes the root tensile strength results from 15 different plant species, which included some from Canadian home garden system. The inversely proportional relationship between root tensile strength and root diameter was observed in cocoa, tea, and coffee plants. Other plant species did not appear to show the inverse relationship, which was discussed in literature. And it is noted that the frequency of root specimen needed to be increased in order to verify this relationship. For a pilot analysis to quantify the effect from plant species, site at Uvavellas University in Badulu Sirigama in Badula district was chosen. There had been slow ground movements in the rainy seasons of 2007, 11, and 12, posing a threat to the community living near the toe of the landslide. A network of surface and subsurface drains was constructed at site in order to arrest any further ground movements. However, at present, the site has areas with exposed bare soil formations, and there is a potential for occurrence of shallow slope instabilities. Therefore, an engineered vegetation cover is of utmost importance in this site to minimize soil erosion. For the pilot analysis, it was decided to use clove species, which offer economic benefits without the need for uprooting, as a possible vegetation cover and determine its effectiveness in arresting shallow mass movements. Information on subsurface profile present at site were obtained from the study carried out by Japanese International Cooperation Agency in 2015. In the analysis, a separate layer was introduced called colluvium after vegetation, which is about 2 meters of thickness. That is the average root depth zone of clove tree. This layer was assigned the modified shear strength parameters from the testing of plant species. The conditions of the slope were then simulated in GeoStudio module considering limit equilibrium approaches to check possible shallow failures. Spencer method was adopted to calculate the factor of safety. This analysis shows that the factor of safety values could be increased further by introducing proper vegetation. These results can be further filtered out with a greater number of data from different samples. With that, we have come to the end. As conclusions and recommendations, I can state the following. This study investigated the influence of root tensile strength on slope stability by computing the shear strength increase or the root cohesion offered by different plant species. The approach adopted in finding root cohesion values could be regarded as straightforward, yet it is an extensive way of ranking plant species as per their potential to improve slope stability. The analysis showed that the factor of safety values could be further increased by introducing appropriate vegetation. However, it is recommended to carry out detailed studies with more number of root tensile tests on individual plant species in order to arrive at more representative values of its root cohesion. Thank you.